All right. So, quick review here. Find the radius of the circle. Okay, well, on number one, the radius is one of the legs of a right triangle. So, since we have a right triangle and we have one leg in the hypotenuse, we can think about this as A, B, and C, because remember, opposite the right angle. And we can just do the Pythagorean theorem. So, A squared plus 12 squared equals 13 squared. So that's A squared plus 144 equals 169. And then you just take 169 minus 144 and you get 25. And when you square root both sides, you get A equals 5. So the radius is 5. And that's actually a Pythagorean triple, 5, 12, 13. Very common one. All right, number two. Again, quick review. We have the radius is the legs of the triangle are the radius. So in other words, they're both equal, which means we have an isosceles, right triangle. And since both legs are equal, and this is our hypotenuse, that means we have a 45, 45, 90. Okay? So if we have a 45, 45, 90, to go from the hypotenuse to the leg, we're going to divide because we're getting smaller. And we got to remember, is it radical 2 or radical 3? Well, just think about it. We have two different angles, 45 and 90, so we're going to divide by radical 2. Then we need to rationalize. So 18 times radical 2 is 18 radical 2. Radical 2 times itself is 2. This cancels, giving us 9 radical 2. All right, so determine if the segment lengths form a triangle. If so, is a cube of 2's or right? Well, we're just going to use the Pythagorean theorem again. That got messed up. So 3 squared plus 7 squared. Well, we're not going to say equals because we don't know. We're just going to leave it blank there. 9 squared. So this is 9 plus 49 something 81. 49 plus 9 is 58. 81. 81 is bigger. We always look from the C, and since C is larger, this is an obtuse triangle. Okay, let's try this. 4, 4, and 6. 4 squared plus 4 squared and 6 squared. So 4 squared is 16 plus 16 and 36. 16 and 16 is 32. 36, also bigger, so this one ends up being obtuse. Now, if that was 5 and 5, then we would have had 50, and it would have been a cute triangle. Okay, on to the new stuff. So, new language. Okay, you already know what a radius is and a diameter. That's nothing new. Radius goes from the center out to the edge of the circle. Diameter goes all the way through the center. New word we're getting here that you may not have heard before is a chord. A chord has 2 points on the circle, like so. All right? A secant, also a new word, is a line that intersects the circle 2 points. So this is just going through the circle. It comes from outside, goes through the circle, and leaves the circle. Another new word is a tangent. Okay? And a tangent is a line in the plane of a circle that intersects exactly at one point. So it just comes by and touches at one point, and this is point B, which is called the point of tangency. Okay, you've heard that word tangent before. Oh, somebody went off on a tangent. Or somebody's talking, and oh, squirrel. They went off on a tangent. Kind of a somewhat related topic, but went off to the side. So tangent is just barely related. Okay, it's just one point touching the circle. Okay, so tell whether these are ray, segment, line. What are they? Are they a radius, a chord, diameter, secant, or tangent? So AC. AC goes from the outer edge to the middle. So that would be a radius. AB goes from one edge to the other through the center, so that's a diameter. DE, now notice it's a ray, okay? So DE is on the outside of the circle. It doesn't go through the circle, it just touches at one point B. So that's a tangent. And B is the point of tangency, in other words, where it touches the circle. And then conveniently, to get all of them in, AE goes through the circle. From the outside, through the circle, and out the other side. So that makes it a secant. A little vocabulary there. Oh, more vocabulary, yay. Okay, so coplanar circles and common tangents. Okay, coplanar. The plane is your piece of paper, the desk, any flat surface. Okay, so two circles can intersect at 2 points. Okay, kind of like a Venn diagram. Okay, 1 point right here and right there, whether the one circle's inside the other or one's outside the other. Okay, they're just touching at 1 point. Or no points. Okay, and we have this situation where just two circles, nowhere near each other, not touching, nothing. Or we have a very special no point of intersection, like this, concentric circles, like a dartboard, where they have the same center. Okay, so a smaller and a bigger circle, basically similar circles, with the same center. Okay, next, a line or segment that is tangent to two coplanar circles is called a common tangent. Okay, so right above in the red, we have a common tangent because the tangent line has a point of tangency on both circles. Okay, common internal tangent intersects a segment that joins the centers of two circles. And a common external tangent does not intersect the segment that joins the center of two circles. So just more vocabulary that you get to get down with. We have time. Okay, tell how many common tangents the circles have and then draw them. Okay, so on A, it's going to be a little weird at first, and I don't know if my smartboard is going to cooperate. I can draw a tangent line that just touches at 1 point here and here. Okay? I can also do that below. And, well, that worked pretty good. Right there and there. So there's two lines of tangency right there. Now, of course, I didn't pay attention to my own example. So first off, I've got to connect the centers. So here's my centers. Okay? Now, I'm supposed to do blue for external. So here's blue. These lines should be blue. Why? Because they're tangent lines, but they don't cross the connecting line. So they don't cross that black line, do they? Okay? I can also draw tangents like this. Okay? So, you know, they touch right here and right here. And then I can draw a tangent line that just touches there and just touches there. Again, now it's kind of hard to draw on the smartboard, but you can hopefully get my point. Okay, now since those cross that black line connecting the centers, those are internal common tangents. Okay, so I'm going to draw my connecting points first. Okay, now my blue, my external, easy. Again, kind of just go on the outside. 1, 2, just touch the outside. And now the only way to touch a common one, since these are touching circles, the only way to do this is right here. Okay, so I have 3. 2 external and 1 internal. Back to this one, okay? Back to black, right there. Now, on this one, again, I can just go outside and hit 1, 2. Now, I cannot do an internal one because there's no way to draw a straight line that touches both edges of the circle since they're overlapping. So in this case, I only have 2. All right. So another new theorem: tangent line to circle theorem. So in a plane, piece of paper, if a line is tangent to a circle, if and only if the line is perpendicular to a radius of the circle as endpoint. So the first example, QP is perpendicular to line M. And then the congruence theorem says tangent segments from a common external point are congruent. So if you have this point out in space, S, a tangent line to the top of the circle and to the bottom of the circle are going to be equal. And remember, those lines are only tangent if they form a right angle with the radius, like so. Not perfectly drawn, but you get the idea. Okay, so in example 3, is ST tangent to P? Okay, circle P. Well, that's only if ST forms a right angle with PT. Which basically means we need to prove that this is a right triangle. So, 12 squared plus 35 squared has to equal 37 squared. Okay? Now remember, in this case, we're trying to prove this is a right angle. If that's the right angle, then this is the hypotenuse. Not to mention it's also the longest side, so that's why 37 is C. So this is 144. 35 squared is 1225, and 37 squared is 1369. So we have 1225 plus 144, we get 1369. 1369, check. So the answer is, yes. It is tangent to the circle. Okay, in the diagram, point B is a point of tangency. Find the radius of R of circle C. Same concept. We're trying to prove this is the right angle right here. Got ahead of myself here. Okay. So, trying to prove right angle, this is the hypotenuse right there. Now what's confusing is it looks like the hypotenuse might be 50, which wouldn't make sense because down here we have 80. And the hypotenuse has to be the bigger side. But remember, this 50, or no, not remember, but notice that this 50 only covers from A to the outside of the circle. Then it also has the radius along with it. So 50 plus R is the actual hypotenuse. So when we go to do this, okay, sorry, trying to get the line right. That's not the right choice. Never mind. Okay, so we're going to do R squared plus the other leg, which is actually R plus 50 squared, equals, nope, that did the same thing I didn't want to do. Sorry, that is the hypotenuse. So R squared plus 80 squared equals R plus 50 squared. Okay, my mistake. So one leg squared plus the other leg squared equals the hypotenuse squared. So this doesn't change. It's R squared plus, well, 80 squared, so that's 6,400. Equals, now over here you gotta just do a little bit of algebra. So we're multiplying, distributing, FOILing, whatever you want to say. Okay, so we're gonna get R squared, first times first, outer times outer, 50R, inner times inner, 50R, and then last times last, 2,500. These are going to simplify. So what we get is R squared plus 100R plus 2,500. So here's why it doesn't end up being as bad as you think. If you subtract R squared, these actually cancel. Now you just have to move the 2,500 over, and you get 100R equals 3,900, and then we divide by that, R equals 39. So the radius of that circle is 39. And now that makes sense. 50 plus 39 is 89. And that is bigger than 80. And if you want to prove it, I'm not going to spend the time here, but if you wanted to, you could do 39 squared plus 80 squared equaling 89 squared. And you could prove that that is the right triangle, or that you did it right, which we did. Okay, example 5. RS is tangent to circle C at S, and RT is tangent at T. So basically, you have a point out here in space. This line here, tangent here, this line here, point of tangency there. These have to be equal to each other. So we just set them equal to each other. Subtract the 4. Divide by 3, and x is 8. And that is all there is to it. Finished.